Well, thank you very much for having me. Hopefully everyone can hear me fine. I think the room's small enough. So I've gone for a slightly catchy title, if you like, but it's more of a personal journey because my background is astrophysics. Now I don't work on any astrophysics aspect at the Met Office, but I'll apply a lot of the techniques and the skills and knowledge that I acquired in my astrophysics career. So I thought it'd be good for me to talk about this idea that there is life after astrophysics as well, if you choose to do something like that, and continue to do science, which I would obviously encourage you to do so. So this is just a quick outline of like where I started, which was the relativistic physics and the radiative transfer aspect of that. And I will finish with talking a little bit about what I do now in terms of my day job and what I've been doing at the Met Office. So if there's anything I don't explain very well, please feel free to jump in and ask any questions. I'm happy to be interrupted on that respect. Okay, so this is a quick, it's a artist impression, just let me clarify that, of the kind of systems I used to work on. So the one on the left, this is something called an X-ray binary. So right at the center of that picture where these red streams, or what they call jets, are coming out, you would have a black hole, which would be the size of, say, 10 solar masses. So it's a small black hole. And there's a star next to it, which is called the donor star. So the black hole is stripping material from the donor star, and as the material is falling into the black hole, a lot of energy is released, which is in the form of this accretion disk, and there's also these relativistic jets that are coming out of that. Wherever you have this type of accretion, accretion is just any process where the matter is falling into the black hole. It could be a neutron star as well, or it could be a white dwarf, anything that's really, really high gravitational field that's present. Wherever you have accretion, you end up with jets. So there is this relationship between accretion and ejection, if you like. It's quite a universal thing, and this is something we still don't fully understand, why you end up with this kind of relationship. My focus was on actually the jets, so trying to understand these high energy jets coming out of these systems. And the picture on the right, that's actually a galaxy. So it's obviously a picture of a galaxy in terms of impression of one. So you have almost exactly the same kind of setup. You have a black hole at the center of a galaxy. Almost every single galaxy in the universe will have a black hole at the center of it. In this case, this is a supermassive black hole. So this will be something like 1,000,000 times the mass of our sun. But you still have accretion, so you're going to have matter falling into the black hole, and then you're going to have these jets coming out of it. Luckily for us, our galaxy does not have an active black hole, so there is no matter falling into the black hole, so we don't have an active galactic nucleus. So AGN is active galactic nucleus, and because if you have one, then life would be pretty tough to exist in that galaxy. It would just be bombarded with radiation to the point that you might have a very strange life form, perhaps, I don't know. So that's basically what I used to work on. For my PhD, I did X-ray binaries, small black holes, and for my postdoc, I did big black holes, but still looking at the jets. The physics is pretty much the same. It just depends on the mass of the black hole, and also whether you're looking at the jet sideways or if it's coming straight at you. It has very different properties because of the fact that you have these things moving really, really fast. I mean, we're talking about nearly 0.9 of the speed of light, so you have really strange effects starting to take place. So that's where the relativistic effects come into play. So I talk about relativistic energy, relativistic effects. So this is your famous E equals mc squared equation, but this is in the relativistic form. So the equation one is that, but you have this factor of gamma in there. So the gamma is what the bit that makes this the relativistic form of it. We don't need to worry about the details of it, but the point is, if you look at equation 3, you have E equals mc squared. That's your classic form of that equation. Plus you have the relativistic aspect of it. So the gamma bit is where you have the speed of the particle or the body taken into account. And a system becomes relativistic when its kinetic energy, which is the bit that's gamma minus 1 mc squared, it becomes about the same as its rest mass energy. So you have to start worrying about its kinetic energy and the impact it has on its properties. So that's literally 30-second introduction to relativistic physics, I guess, if you like. I mean, that's where you start having to worry about these things. So the gamma is the key thing here in terms of relativistic physics. And the radiative transfer processes that I was looking at as far as the relativistic systems are concerned, there were two, Compton scattering and synchrotron radiation. Now, the picture on the left is Compton scattering. So that's when you have a photon interacting with an electron and it scatters off it. So depending on the energy, the amount of energy you have in the electron and the amount of energy you have in the photon, you end up with either a high energy photon or a high energy electron. But the principle of it is that you have electrons interacting with photons, and that's your scattering phenomenon. And the one on the right is the it's the synchrotron radiation. So actually, this is the same thing that takes place at I don't know if you're familiar with Diamond. There's a light source up in Oxford where they're doing a lot of work on protein profiling, and there's the research going on, and they need to produce really high energy X-rays to be able to penetrate cells and trying to picture, if you like, proteins. And the way to produce really high energy X-rays is by taking an electron and you accelerate it really fast in a cyclotron. So similar to the Large Hadron Collider, where they accelerate protons, but in this case you have electrons. And as electrons moving really, really fast, I mean, as we start approaching the speed of light, just the sheer act of acceleration in the presence of a magnetic field causes them to emit photons. And these photons are really high energy and they're really focused. They will be focused in the direction that the electron's moving in. So that's the way you can generate really high energy X-rays from electrons. So that's exactly the same principle that takes place at this diamond light source in Oxford. But this also takes place in these jets that I was talking about, because you have really high energies, you have really fast moving electrons and protons and all sorts of exotic particles, and you have really strong magnetic fields on top of that. So you're going to have these the synchrotron radiation taking place. So you can think of jets as cosmic accelerators, if you like. In fact, they are the biggest accelerators in the universe. Now, the radiative transfer bit is just a fancy way of saying, you know, you have this much light going through some body or some kind of volume, and how much is it absorbed, how much is it scattered in different directions, and how much of it goes straight through. So that's all that is. That's the equation on the right is saying. You're saying, what's the change? So I is your intensity, the amount of energy, the amount of light you have present. How much of it is absorbed? So that's your extinction. So you subtracting that's the minus sign there. And how much of it is actually emitted? So you have, it's the same principle as a heater, right? I mean, a black body. Anything that has a temperature, anything above absolute zero, emits radiation. So that's the fundamental thing. So whenever you're doing radiative transfer calculation, depending on your frequency, you're trying to work out, you have this much energy coming into the system, how much of it is getting absorbed, and how much of it is being added, depending on what the system is. Because, for example, you could have a volume where it's at 30 degrees, if you like, centigrade. But if you have just really like dim, like infrared light shining on it, and you're trying to view that through the other side of that box, you're not really going to see that, because the whole thing is going to be completely like outshone by the box itself, because that's emitting way more than what's coming in. So that's where the plus rho J bit becomes important. So it's always this balance of emission and absorption with rates of transfer. I'm not sure, to be honest, if we need to go into that kind of detail. If this is just to say you can just rejig the equation in the form of something called optical depth. Optical depth is just your measure of a substance's ability to absorb the light. That's all it is. I think we definitely will skip this bit. Actually, I put that over. I think it was an unnecessary detail. I wasn't sure how to pitch this one, but yeah. Okay, so actually that's probably a good time to say, look, let's come back down to Earth. Okay, where am I now? What am I doing? So this is just like, again, a little bit of schematic in terms of what happens in Earth's atmosphere. So this is showing you, the top bit is showing you atmospheric opacity, just like how opaque the atmosphere is for a given wavelength. So if you look at where the rainbow pattern is, the atmospheric opacity is pretty low. So what that's telling us is that in that wave band range, the atmosphere is quite transparent, and hence we can see everything, right? I mean, that's why we evolved to be able to see in that band. So, but you can see that in shorter wavelengths, it's actually really opaque. So that's again a good thing, because UV gets absorbed by the atmosphere, so we're protected by our atmosphere mostly. And if you look in the radio waves, which is like much further down, 10 centimeters to 10 meters, it's completely transparent. So that's why you can observe this. You can have radio telescopes on Earth working quite nicely. You don't need to go into space like Hubble telescope, because even though it's pretty transparent, the Earth's atmosphere, but it's not completely transparent, so you can see that it's not zero. So that's why if you want to have a much clearer picture, you need to get higher up in the atmosphere to be able to see through it. So that's basically my work, because you're trying to work out how the radiation coming from the sun is impacted by Earth's atmosphere, and what impact that radiation has on Earth's atmosphere. Because a lot of this energy, so where it is opaque to the particular wavelength, the atmosphere is absorbing all that energy and redistributing it. So that's where you have to take those processes into account. For example, climate projections, so CO2 or other greenhouse gases, that's a classic example of they absorb energy in one particular wavelength and then re-emit in another wavelength, and that's where you end up with this trapped energy within Earth's atmosphere. And then you also have scattering. That's also important to take into account. It's not just about the absorption. Scattering is anything of something like aerosols. So you're going to have emissions from like factories, and you can have carbonate particles. So scattering is just more of a case of redirecting the light rather than absorbing and re-emitting it. So it starts becoming quite complicated pretty quickly. So you need to take all these processes into account. So this is, I mean, I don't expect you to like be able to read any particular detail there, but this is to show you that you have wavelength and you have transmission on the y-axis and the wavelength on the x-axis, and that's the way Earth's atmosphere works. So you're going to have really, really fine absorption lines or emission lines, if you like, within the Earth's atmosphere. So if you're working on a really, really high resolution, this is how you would the electromagnetic spectrum would look to you. That's how spectrometers work, right? I mean, you know, a particular gas or particular material has emission and absorption at a very particular a particular wavelength. So you can work out what the material is just by looking at its emission spectrum. But these things become important when you start looking at broad wave bands, because you're going to have net absorption and emission taking place. So yeah, I guess it's just more of a like a zoom in of this, basically, that you have in say 2 to 28 microns, is a 10 to the minus 6 meters, the wavelength. You have very particular behavior depending on what kind of gas you have in the atmosphere. You have water doing a particular thing in terms of transmission, and you have CO2, you have O3. So, and to get that right is important because it all contributes to your energy budget. That's where it's important to get your energy budget right. Not necessarily for your weather prediction, because the model I work on in the Met Office, it's used both for weather prediction but also for climate predictions. Now, for a 1 day, 2 day forecast, a tiny difference in solar energy may not make a difference. But if you start doing 50-year runs, 100-year runs, a small difference can really add up. And so you need to be careful about these things, and you need to be confident that any inaccuracies, I'll say the word inaccuracy because there's always this trade-off between the speed or the efficiency of a model versus its accuracy. You need to make some approximations. You can't have a perfect model because you'll be waiting forever for it to run, so you'll never have any type of forecast. So you need to be confident to say, look, we are approximating this by using this, but what's the difference, and how much of an impact does it have on your predictions and your forecast? So that's really the crux of my work, to profile what the approximations do, and then see if there's a way to make it better, but at the same time it needs to be efficient. So this it's quite a challenge, but it's given me a job. So going back to the radiative transfer equation, so if you recall that, it's just a balance of these things. This is just giving you the same thing, but now you have absorption and scattering taking place. You're going to have all the different gases I showed you, like the spectrum that has, you name it, all the gases are present there. And then you have aerosols, which are much bigger particles, and they're scattering. So all of that needs to be taken into account. So that's where the complications come into it. That's what I guess the devil is in the detail. That equation by itself is relatively simple to solve, but once you start drilling through in terms of what the different components are, the problems arise. And this is all assuming something called local thermodynamic equilibrium. So this is just to say, if a body is at a certain temperature, it will emit like a Planck spectrum. Those with physics background will be more familiar with it, but it's just you have a relationship between the temperature of a body and the amount of radiation it gives off. That relationship starts breaking down as you go higher up in the atmosphere, especially when you start getting to the thermosphere and beyond. That's where you have a non-local thermodynamic equilibrium, because it's not many gases present, so you end up with it becomes a lot more of a chemistry problem actually at that point than necessarily a physics one, if you like. So I'll stay clear of that. I'll stick with physics. Oh yeah, so this is actually well, I've kind of whizzed through it really, I guess. It's the final slide actually. So this is actually something I worked on just to give you a taste for application of things. So this is something called NEON. This, don't ask me, it's an acronym and I can never remember what it stands for. But the point is, this is used by the defense sector in terms of, so the observer is someone in a plane, and they want to know whether they'll be able to see this pickup truck with a nasty thing on his back. And they will come to us and say, look, this is the place, this is the time, am I going to be able to see this vehicle, this building, whatever you like. So that's where the radiative transfer modeling is important, and to get it right, because there's a lot of things happening here. You're going to have different bits of radiation that are going to be heating up the vehicle in different ways. The vehicle's made up of different materials, so which will heat up differently, and then the ground is going to heat up differently. So you end up with something called a temperature contrast, and that's what you rely on. You know, we know contrast is how you see things. So in the visible, you're going to have black and white, say, and that gives you a very perfect contrast. In the infrared, which is how a lot of the sensors work on planes, you need temperature contrast for you to be able to see. So you're going to be some kind of resolution there, so that's going to happen. But then you're going to have the infrared signal coming from the vehicle, and the ground and everything else is going to be going through the atmosphere, and it's going to be absorbed by the rain, the gases, going to be scattered. So the signal is going to be quite small by the time it gets to the observer. So this is the kind of the application, I guess, of radiative transfer, other than obviously the weather prediction and the climate stuff, that you can have much more day-to-day, if you like. Well, I guess not many people are interested in that kind of thing. It's more of armed forces, but yeah, but you get the idea that there's a lot you can do with what I'd say is the same physics, really. So I just wanted to give a take-home message that, you know, learn physics, get your physics right, and you can apply it in all sorts of different scenarios. And I'll leave it there, actually. So if you have any questions.